This is the last slide of section 4-3. Okay? It talks about the effects of anomalous GDD and SAM. GDD is the group delay dispersion, and the SAM means self-amplitude modulation. So the figures are a little bit different from those we have seen in the previous slides. Now the horizontal axis means the normalized dispersion. So the left half means the anomalous dispersion. Right half means normal dispersion. And in the first figure, the vertical axis is the pulse width. So you see two curves. The blue one means the behavior when SAM coefficient is 1 unit, gamma 0. The red curve is the case when SAM coefficient is increased by 15%, 1.15 gamma 0. So you see very different behaviors between the left half and the right half. In the right half, meaning the normal dispersion area, you see the two curves are separated. And the blue one is worse than the red one because the blue one corresponds to broader pulse width. Okay? So it's quite intuitive because when SAM coefficient is larger, the pulse shortening effect is supposed larger. So you can have shorter pulse width, the red one. But in the left half, it is very different because now the two curves are almost overlapped with each other. That means the increase of SAM coefficient does not help in giving a shorter pulse. Okay, no matter it's gamma 0 or 1.15 gamma 0, you almost have the same pulse width. Okay? If you observe the second or the middle curves, okay, you see the red one is still better than the blue one because now the bandwidth is broader if your SAM coefficient is larger. It's also intuitive. Okay? But it's more symmetric compared with the first figure. So that means bandwidth response is less obvious compared with pulse width response. Okay? If you observe the third figure, it's also very evident. You see on the left half, the two curves, the blue one and the red one, are almost overlap with each other. So it also means SAM coefficient does not change the chirp rate in steady state if you are working with anomalous dispersion regime. Okay? They share almost the same steady state chirp rate. But in the normal dispersive regime, they are separated. So if you have a larger SAM coefficient corresponding to the red curve, your steady state chirp rate is smaller. That means closer to chirpless, which is better. Okay? But in the anomalous dispersion regime, SAM seems to play a secondary role. It's not very important, only secondary role. So pulse parameters are nearly insensitive to the SAM coefficient gamma if anomalous dispersion exists or D coefficient is negative. Okay, left half in each of the three figures. And in fact, pulse shortening mainly comes from the interplay between cell phase modulation and anomalous group delay dispersion. In lesson 3, we have known it results in the so-called soliton effect. Okay? Do you still remember the soliton effect? If the SPM happens to cancel with anomalous GDD, okay, a pulse can propagate for a very long distance without distortion. It can maintain the shape and propagate for long distance. Okay? So it's not only useful in terms of pulse propagation, but also in pulse formation. You can regard soliton effect as a force to create a short pulse and then maintain the short pulse. Okay? While the SAM only stabilizes the pulse after its formation. So the pulse is formed by soliton effect, then stabilized by SAM. Okay? It still helps to stabilize the pulse against the noise perturbation. 那为什么？其实也很直觉啊。SAM 是一个让 pulse peak 留下来 ，pulse wing 压抑的机制。Whenever you have noise perturbation, it plays an important role in pulse wings, but can be suppressed by SAM if the SAM coefficient is bigger. But in these three figures, we cannot observe the stability. We only observe the steady state parameters. Okay, so the SAM coefficient, its effect is less obvious in these three figures. Okay. And it also highlights another category of femtosecond pulse generation techniques. Okay. Here, in our simulations, we assume the materials are lumped crystals. Okay? 意思就是我整个共振腔里面有材料，但那个材料呢，通常是薄薄的一些晶体。Okay? For most of the time, the pulse propagates in the air instead of in the material. So it's a lumped parameter model. Okay? So the simulation applies for solid-state femtosecond lasers, like Tysavvy lasers, neodymium YAG lasers. Okay, these models work well. But in fiber lasers, it's very different because in fiber lasers, your pulse always propagate inside material, the optical fibers, right? So the lumped parameter model is no longer valid. The simulations here are no longer valid. 在那个情况下呢，你的脉冲几乎都走在材料里面，它的 interaction 呢，你不能再把它看成 lumped， 就是偶尔通过一下下，不是，你就要做很复杂的计算，你的计算随时要保持，同时考虑 SPM 跟 GDD 的 interplay，OK。好，那这样子的状况呢，就远非这个模型所能描述。Okay, but in fiber lasers, soliton effect has been used for many years. 也就是说，在光纤雷射里面呢，其实你不一定需要这个 SAM. Maybe you don't need saturable absorber. You just need a piece of fiber. And play in the SPM and anomalous GDD. If they are roughly balanced, soliton effect is very important. Then you can create short pulse from the noisy initial condition. Okay? But usually people still insert saturable absorber inside the fiber lasers for pulse stabilization or for initial broad pulse generation. You know, in the beginning, your cavity has random noise only. The peak power is very low, right? Then the soliton effect is very weak. Your SPM is too weak for the initial condition. Okay? 那你就很难启动你这个 pulse formation. So you need a weak SAM to create a broad pulse. Okay? To increase the peak power a little bit such that solitone effect is strong enough for pulse formation. And after that, you can even remove the saturable absorber and the pulse is still there. Okay? 所以它扮演的角色其实就变成稳定你的脉冲，而不是形成你的脉冲。Okay. So this is an extra comment about the real situations. Okay. Any question? In the last section of this lesson, we would like to make detailed analysis about curve-length Morlock Ti-sulfide lasers. Okay? The reason is Ti-sulfide lasers are very important laser engines in real applications. And I can show you some details about how to design Ti-sulfide lasers. And the same idea might be able to be applied to other lasers. Okay? So this is an example of demonstration. We will start with the simple schematic and the basic idea of Ti-sulfide lasers. We will try to calculate the SPM coefficient and the SAM coefficient. Why? Because in our master equation, these two coefficients are necessary if you want to know the steady-state pulse parameters. You need the two coefficients. In our modeling, they are just two numbers. You don't know how to get these two numbers in real laser systems. And here, I will show you how to do that. And finally, the linear and the nonlinear cavity analysis to get all the parameters you need in the master equation. Okay, the idea is very simple. Okay, say you must have some crystal inside your cavity, like you have Ti-sulfide crystal as your gate media, right? And you have curve lengthening effect in the gate medium itself. Okay, so that means you do not need an independent saturable absorber for your cavity. The gate medium itself can serve as saturable absorber as well. 所以一个材料就扮演两个角色，既可以用来放大光，又可以当饱和吸收体。Okay. What happens if you have curve lengthening? As we introduced in lesson 3, the idea is quite simple. Your pulse peak has stronger peak power, and in the presence of curve lengthening, what happens? Your beam size will be reduced, right? Because of the stronger wave guiding effect. The index is increased by your laser beam itself. So the central part has a higher index than the surrounding part. So it's a wave guiding effect. And the pulse peak intensity is stronger. The guiding effect is stronger, so you have a narrower laser beam. For your pulse wings, you have a broader laser beams. Okay? But how to take advantage of this curve lengthening effect to get a pulse shortening effect? Because without doing anything, this phenomena does not naturally, automatically give you a pulse shortening effect, right? 你只知道 peak 有比较细的beam, wings 有比较粗的beam, 不会自动帮你做脉冲压缩嘛？如果你什么也不做，它只是一个 fact, it's a phenomenon there, but it does not help in pulse shortening, right? How to truly shorten your pulse? As we discussed earlier, you can insert an aperture like this. Okay? In this case, your pulse peak passes through the aperture totally, but your pulse wings are partially cut by your aperture. So pulse wings experience a stronger loss than the pulse peak, and you can have pulse shortening effect. And this is a mechanism transforming self-phase modulation into self-amplitude modulation. Originally, it's totally phase modulation, right? Index change is only a phase modulation. But with the insertion of an aperture, the transformation is carried out. Now, it's no longer just phase modulation. It's transformed to amplitude modulation. And you can see this simple arrangement. There is no limitation about response speed, right? As long as your Kerr lensing effect is faster than your pulse width, which is generally true because we have mentioned Kerr effect, the N2 coefficient, response time is as short as 1 femtosecond. It's shorter than the pulse duration you can generate by a Teisabi lasers. Usually it's maybe 20 femtosecond, okay? Then this aperture does not introduce any slowdown of response, right? It's an immediate response. Then this self-amplitude modulation effect is essentially instantaneous, okay? 它就变成一个几乎可以看作瞬间的这个 amplitude modulation， 没有速度上的限制。Okay? And it's an artificial fast Sechenov absorber. Artificial means there is no real material whose response time is faster than your pulse duration. But in this design, this is a design in your laser cavity and exploring the instantaneous Kerr lensing effect, you achieve an artificial fast Sechenov absorber. Okay. Any question? 好，所以材料上做不到的，就用雷射共振腔的设计来达成它。但是不要忘了，它其实还是受限于材料哦，受限于哪里？这个 Kerr lensing effect. If your pulse, maybe in the future, if your pulse is shorter and shorter, less than 1 femtosecond, for example, and faster than your N2 coefficient response, in that case, even this scheme cannot give you fast Sechenov absorber anymore. 它还是受限于这个克尔效应的速度，只是对于目前已经存在的 laser 来说，克尔效应够快，它是 fast。可是未来如果你的脉冲越来越短，它就不一定。Keep in mind, there is still physical limit there. Okay, now we need to do some calculations. Starting with the formula of post-Gaussian beam. Actually, we have seen this model before. A post-Gaussian beam, the light intensity, big I, can be written as the product of two terms. The first one, I0, is the on-axis light intensity. The second term, you can see, is a Gaussian function. Variable small r means here, the radius. Okay, so the second term describes the cross-sectional intensity distribution is a Gaussian function. Okay, and the W is the beam radius. Okay, but what is the on-axis light intensity? Here I have to introduce a new variable T prime. Okay, T prime is T minus Z over V. V is the group velocity of the light. Okay, so you can see T prime actually means the relative position of the pulse, just like the left figure here. Okay, for example, T prime equals 0 always indicates the pulse peak. Okay, here This is the pulse peak, corresponds to t prime equals 0. But t prime is not a fixed time instant. You see, when z equals 0, if you observe here, okay, z equals 0, then t prime equals 0 if t is 0. But if you shift the observation position to some non-zero z, like here, okay, then the pulse peak t prime equals 0 occurs at a time instant no longer 0, right? It's equal to the z over v. It's shifted by amount determined by the shift of your observation point. OK， 好，所以这个 t prime 的好处是什么？它就变成一个什么？跟着这个 pulse 一同用 group velocity 前进的一个坐标系。好，那 pulse 的相对位置就不会因为 t 跟 z 而不断的改变。你 fix 一个 t prime， 你就 fix 了 pulse 的相对位置，方便我们指定 now it's pulse peak or it's pulse wing. That's the reason. Okay. I0, as I mentioned, it's on axis light intensity, so it's equal to the power distribution of the pulse divided by the beam cross-sectional area. Okay, power divided by area, it's intensity. Okay, and the power is described by P of t prime. So P of t prime can specify the pulse shape. Like this case, it's close to a Gaussian shape. But in reality, you can specify P of t prime as a triangular shape or square shape, whatever. It can be used in specifying the pulse shape. But beam cross-sectional area is, the formula is fixed. It's here, pi w squared over 2. Okay? W as a function of z is shown here. You can tell it is the famous Gaussian beam formula, right? Where B coefficient is so-called confocal parameter, equaling pi n w0 squared over lambda, also according to the Gaussian beam formula. Okay? So you can see the beam size is smallest here, right? When w equals w0, the waist radius at z equals 0. So your on-axis light intensity is strongest when z equals 0. And when z is bigger and bigger, your beam radius is larger and larger, and your cross-sectional area is bigger and bigger, so your on-axis light intensity will decrease with z. Okay. So that's the general picture. On-axis light intensity depends on two factors. One is the beam cross-sectional area governed by the Gaussian beam formula, increases with z, basically. The other factor is the pulse shape. Okay? Your pulse peak has stronger power, peak power, light intensity is stronger. But if you observe a pulse wing position, your P of t prime is smaller, on-axis light intensity is smaller. Okay, so on-axis light intensity depends on both factors. And finally, I make an extra remark. The beam radius W is independent of t prime. See our formula. W is a function of z only, not a function of t prime. So what does this imply? It implies here we don't consider Kerr lensing effect for the time being. T prime means the relative position of the pulse. Okay? So if W is independent of T prime, it means it does not change with pulse peak or pulse wing. So currently we assume the beam size only changes according to the linear Gaussian beam model in the absence of Kerr lensing. In the future, Kerr lensing effect will be independently taken into account in other places, not here. Okay, so this is one extra comment.